Alright, so I'll go ahead and start. My name is Brian Duggan, and I'll be talking today about informal domain-specific languages in Perl 6. Thank you all for coming and attending this talk. A little bit about my company. I'd like to thank Craftworks for sending me here. We're a consulting company in Philadelphia. We do coding in a lot of different languages for large and small companies. Okay, so this talk is about domain-specific languages, or DSLs. But first I want to clarify the informal in the title of the talk. So if you look for the definition of DSL on Wikipedia, you'll see a lot of languages like HTML or SQL. These are all DSLs. They're languages that are focused on a particular domain, but they're not. DSL has also come to be used in a lot of other ways. So these days when you're writing an application that generates HTML, you'll have your own language that generates this other DSL. So those are the languages that I'm talking about. So the same thing is true for SQL. You don't usually write your SQL by hand these days. You'll have your own framework that helps you generate it. And the little framework and the nuances of that are often called DSLs. So those are the informal DSLs. They don't have specifications, even though they're languages. They're restricted to small communities, and they change a lot, but they're very practical, and they're the things that you type by hand when you're writing programs. A few examples, so templating languages. If you look on Wikipedia, I think you'll see about 100 different templating languages these days. You've got wiki languages, markup languages. Markdown is popular, but there are a lot of different flavors. There's GitHub Markdown. There's Wikipedia's Markdown. For SQL generation, we have ORMs. There are also a lot in different languages. In Perl, there's DBIX class or rows. In Python, SQL alchemy. In Ruby, there's Errol. And these are all ways of avoiding writing SQL. But you still have your own little isolated informal DSL to generate these languages. Web microframeworks are another example. The cute syntax that you use to generate your routes, where you say get this, post that, and it generates routes. Those are also informal DSLs. So in 2010, Martin Fowler wrote a book called Domain-Specific Languages, and he divided them into two different categories, internal and external. Internal DSLs are languages that are a subset of a more general programming language. And external ones are languages where you're actually parsing it. So you have some sort of parser, but it's not just a subset of Python or a subset of Ruby. I'm adding a third category to this talk, which I'm calling variant DSLs. And these are languages that start off as a more common language, but you modify it a little bit. And in Perl 6, there's a notion of slangs, which refers to this concept. So for each of these categories, internal, external, and variant, I'm going to talk about a Perl 6 technique that can be used to create informal DSLs in this category. We'll start with internal. I'll pick an example from each one, and then an application of the technique to generate a language. Okay, so we'll start with internal, informal, domain-specific languages. So mouthful. Okay, and what we're going to talk about are the Perl 6 custom operators facilities. Okay, so a quick review and explanation of the different types of operators that you see. These are the types of operators in Perl 6. You have infix operators, which have their arguments on the side. You have prefix operators, like the minus in this case goes before what it's operating on. You also have postfix, like A++, which operates on the thing before it. Circumfix, or around something, and post-circumfix, like taking something out of an array. So these are all the different types of operators. And you can see that some of them take one argument, some of them take two arguments, right? So infix and the prefix and the postfix each take only one argument. After all, they're really just functions. And circumfix takes one argument. Infix and post-circumfix take two arguments. So already, even though you can write A plus B, you can also use operators in what's called a noun form. So if you take the plus, and you put some brackets around it, and you put an ampersand in front of it, then instantly you've turned your operator into a function that takes two arguments. And conversely, you can go the other way. So if you have any subroutine that takes two arguments, you will automatically have an infix operator. So here we have an example of saying we make a subroutine called plus twice, which takes the first argument and adds 2 times the second argument. And you can call it with the arguments afterwards, but you can also put an ampersand in front of it, put brackets around it, and then you can say 1 plus twice 2. So out of the box, without doing anything crazy, you already have some interesting constructs for any subroutine that takes 2 arguments. But, of course, what you really want to do is take symbols and use those as arguments. You don't want to put brackets and ampersands everywhere. And to do that, you can define an operator using this syntax. So we say sub infix colon and then less than, and then the operator goes in between the angle brackets, and then you say the operators. So if we want to say, I'd like to use the word plus to add 2 things together, we say sub infix plus, and it returns x plus y. And then you can say 1 plus 2. You get 3. So you can do other things too. Let's say you want to make a prefix operator at, or postfix operator plus plus plus, okay, which modifies the argument, then adds 3 to it. So here we have z equals at 10, and then we say z plus plus plus. So what's it going to come out to? Somebody say 23, right? So first it's multiplying by 10, multiplying by 2, and then adding 3. Okay, so this is not making things easier using operators like this. And you're going to quickly run out of things, and you'll probably end up with obfuscated code. But luckily, we're not restricted to just these ASCII operators. We can use any operator from Unicode. So let's say we wanted to find the dot product. As you may remember, the dot product of 2 vectors or 2 arrays, you multiply the corresponding elements together, and then you take the sum. Okay, sum from 1 to n of the corresponding elements from each array. That's the dot product. And there's an operator for it. It's a dot. We can define the dot product. Sub infix colon dot is, and this is. I won't go into this too much, but essentially we're multiplying the corresponding elements and adding them all together. And then if we say 1, 2, dot 3, 4, we get. See, people are paying attention since it's a lunchtime talk. 11. 11. All right. What about this? So here we can also use their Unicode floor characters. Don't you hate when you have decimals in your code? You have to deal with like floating points or rational numbers. So let's define a circumfix floor operator. Say floor of 2.4. This one is 2. Okay, so what happens if we have several operators and we start using them together? So let's say we have a plus operator here, the word plus, and a times operator, which is the word times. We say 1 plus 2 times 3. What do we get?
Trouble.
Yep. Trouble.
Cobalt.
Oh, cobalt.
Cobalt.
Okay, so I heard 1, 9, and 1, 6. So 1 plus 2 is 3. 3 times 3 is 9. So we wanted to get 7, but we didn't because what's wrong? Precedence, right? Luckily, you can specify the precedence of your operators. So if you want to say that Times is a tighter precedence than plus. You add is tighter here afterwards. Is tighter takes an argument. That's another operator. So precedence is all relative. Now 1 plus 2 times 3 is 2 times 6 plus 1, 7. You get 7. So in addition to is tighter, you could have done it the other way around. You could have defined is looser, say plus is looser than times. You can also say is equiv if two things have the same precedence. If you have like a non-transitive precedence, good question. I don't know. Okay, what about chaining operators? So let's say we have this operator to the power, which is, I don't know COBOL, but it seems like it could be a COBOL operator. We want to raise the first argument to an exponential value. So 2 to the power 3 to the power 2, what are we going to get? 64, because it's going to be 2 to the 3 to the 2, so 8 squared. But what's happening here is we have 2 to the 3 to the 2, and it's 2 to the 3 to the 2. But really it should be this way. If we're mathematicians, it should be 2 to the 3 squared. So in this case, what is it that we want to change? The associativity. So luckily you can change the associativity of your operators too. Okay, so if it's right associative, then you say is assoc right. And now 2 to the 3 to the 2 is 5. Okay. Other associativities, you have right associativity, left associativity, non-associative, which will throw an operator, throw an error. You have this thing called chain associativity, which is really cool because the less than operator has chain associativity, so you can say 1 is less than 2 is less than 3, which means 1 is less than 2 and 2 is less than 3. You also have list associativity, which says take all of these things and let me just make a multi-value function that I can operate on all of them at once. The cross product is list associativity. Okay, so let's look back at something simple, subtraction. Let's say we make up and say, oh, okay, we want to define what it means to subtract one string from another string. So we say it's substituting all occurrences of the first string with the empty string. Okay, so we're going to say this is what it means. You take a string and you subtract a letter. It's like deleting all of those letters from the string. So house minus u is hose. All right. So then, what happens when we say 32 minus 2? Uh-oh, not good, right? Now we get 3. So that's unfortunate because we don't want 32 minus 2 to be 3. Luckily, okay. Luckily, we can fix that. We can give types to our operators. To our arguments. So we define the arguments. We say they are strings, stir$x and stir$y, and instead of a sub, it's now a multi. So we have multiple dispatch for functions and multiple dispatch for arguments. So now, when we have a house and a u, which are both strings, and we have 32 minus 3, we get the correct thing. We get host for the strings, but we still get 29 for the
You ever run into problems with that equals 5? I mean, I write programs all the time until 5 where it's not clear until I use it whether it's referred to as a string or a number.
Well, luckily, it's optional. So Perl 6 has, they call it gradual typing or optional typing.
So if you don't put the type in, you could run into problems.
That's right. So it's up to you whether you want to put the restrictions on or not.
We use regular typing on notice, which is if I don't type the signature, it will be the fallback for any other type.
That's right. Yeah. So the signature of the function, in this case, it has types, but you can have multiple dispatch without having types. It will look at the number of arguments, for instance, or named arguments.
No, I mean for the name for the same for example, you are string int, but in other way use the non-type
You can use them with different types of signatures, mixing types and non-types.
So what if I wrote like 0 at lots of places in the arguments?
We'll get to that in a second when we get Okay, so what if we put in things like constants? I think this is what you're saying, right? Okay, so we have strings here as 2 arguments, and that works fine. We subtracted. What if we want to say we subtract an int from a string, meaning we take a few characters off the end, and if we put a constant here, that also takes precedence. So here we can say an escalator minus electricity, and we get stairs. Even though they're strings, we have a more narrow type than the string type. So we get, we can take the A's out of catamaran, we can subtract 6 letters from catamaran, and then 10 minus 5 still works. Okay, here's an example. So Python has this really nice operator, actually. It's called the % operator, and you can use it. There are 2 different ways to format strings in Python. One is with format, and one is with %. Percent one is very nice. It takes a string, and then it takes either a number or a list, and it kind of works like sprintf. So we can make % work like that in Perl 6 if we want to. So here we say when you have a string and a number, we just do an sprintf. If you have a string and a list, you do the same thing. You flatten your list. You pass it as arguments to sprintf. Then we can say this is %d, and it'll put the 40 where the %d is. We can say pi is about 0.2f, e is about 0.2f, and that's the symbol pi, and that's e. And so this works just like that. We get this is 40, pi is about 3.14, e is about 2.72. So let's look at an application of this to some of the examples in the beginning for domain-specific languages. So generating SQL. So some of the techniques that you might see in various DSLs, in various ORMs or ways of generating SQL, you'll see method chaining, where you'll have you keep calling like join or do something like this, and at the end of the day you get your SQL. You'll see operator overloading sometimes, and then more common than not, you see calling it data structure of use, where you've got like, okay, all arrays mean or, and hashes mean and, or you have nested data structures which somehow get turned into SQL. How many people have worked with ORMs or use ORMs sometimes? So you guys know what I'm talking about with some of these constructs. So we have new techniques with some of those things that we just talked about. The operators can, all those operators could be used to generate SQL. So we could write something like this: user plus address, name equals Ed, and full name equals Ed Jones, where we're using equals and we're going to redefine those depending on the type of what's coming in. We can use the circumfix, post-circumfix operator to filter things, and the way we would do that is we would have, for instance, we'd have a table class, and then the infix plus takes 2 tables, so user and address then would take 2 tables and generate something else. Similarly, we could do something with equals and we could say, all right, equals takes 2 columns, or maybe takes a column and a value, and returns a filter of some sort, and then we could do something else. So you have a lot of flexibility if you're designing an ORM or something to generate SQL in Perl 6. But what I think is interesting is that although operators can be used to generate SQL, operators have already been used to express SQL. Namely, before there was SQL, there was relational algebra. So in the 70s, when E.F. Todd came up with SQL, he first started talking about the mathematics behind it and how you would express queries in this algebra. And he had definitions for things like projection, selection, rename, natural join, semi-join, all these things that we now use SQL to express. So what we could do in Perl 6 is, instead of inventing something new, we could reuse some of these operators that already have well-defined semantics for querying data. So, for instance, we could have the infix bow tie operator make a natural join. and then you could say users join addresses like that. And in fact, you wouldn't be making up something new because there's already precedent for the way these operators behave. You could do the same thing with the projection operator, turn it into a select. So project name and age would turn that into a select state. Conclusion of this section is that custom operators are very cool, and when you're making a subset of a language into a DSL, they are a good way to do that in Perl 6. Okay, so part 2 is external informal domain-specific languages. And for this, Perl 6 has a feature a lot of you have probably heard about already called grammars. So some typical examples of external DSLs include templating languages and wikis. And so for the next section, what I'm going to do is take an example of one of these languages, and we're going to go through it, and I'll show you what it's like to write a grammar to parse a language like that. Okay, so the language we're going to look at is called Slim. How many people have heard of Slim? Wow. No Ruby programmers. So Slim is kind of a cool language. It's popular among Ruby programmers, and this is what it looks like. It's indentation based, and it sort of starts like this. It has HTML here, and then you indent a little bit, you get head, indent a little bit more for title, then you can go back for body, and so it's very terse. So it's actually kind of nice because you can type things out, you just indent, and then instantly you get this like nested, this nested HTML comes out of it. You don't have to type any angle brackets, and so it's actually pretty cool. Okay, so let's take a look. First, we're going to look at how we could parse this language, and then we're going to look at how, given the structure that we just saw as an input, we're going to generate a data structure that's the DOM, an HTML DOM. And it sounds hard, but it's actually not too bad. Okay, so parsing a language. So I'm going to go, this is going to be a little bit of an overview, and you can refer to the documentation for more details about how some of these things work. So essentially, Perl 6 has grammars. They're first-class objects in Perl 6. Declaring a grammar is kind of like declaring a class, except instead of declaring methods, you have regular expressions which are associated with the grammar. So we have a collection of regular expressions here. Certain types of regular expressions are called rules, and some of them are called tokens. So if a regular expression doesn't do any backtracking, it's called a token. And if the white space in your regular expression is significant, then it's called a rule. Those are the only differences between rules, tokens, and regular expressions. But they're really all they're all a type of regular expression with additional constraints. So this HTML here, this Slim code here, where we have HTML head, you can sort of see the pattern where you have some indentation, and then you have a tag, and then you may have some text after the tag. So that's basically it for the language. So the top level rule here is one or more lines separated by an end-of-line character. End of line is a series of character terms. So if we parse this particular code, we parse this using this grammar, we end up with a match object. So this is a nested data structure, and the structure looks like the rules that we just had in our grammar. So we end up with a sequence of lines, and each line has a tag, and it may have some indentation. So these can be very cumbersome to work with. So generally, instead of parsing something and getting a big match object, the way to do something interesting with a grammar is to set up things that happen during the parse. So the way you do that is essentially, so a grammar can basically have an object associated with it, and then every time a particular rule is reached, the method of the same name on that object gets called. So if you have a method called line, if you have an object with a method called line, then while it's parsing and hits a line, it calls your method, and it sends you the current line.
Sends you the current.
It sends you the current line. So here we have our grammar, which had tokens, tags, text, and indentation. And we're going to make a class that has similar methods, one called tag, one called text, one called indentation. And basically what we have to do is say, here's what you do when you see a tag, or here's what you do when you see indentation. And then creating a new object, we say my$dom equals dom.new. We call slim.parse, and then the actions parameter sends the object whose methods are going to be called. Okay, so here is our algorithm for parsing slim. We're going to go through this indentation-based format, and we're going to keep a stack of this. And we're going to have a little node class that's got parent nodes and child nodes, so basic data structure that's a tree. Okay, and when you see a tag, you push a new node onto the stack, and when you see text, you're going to add some text to your node. Then when you see indentation, you pull it off the stack. Okay, so this sounds a little confusing, so what we're going to do now is walk through an example of seeing this algorithm at work before I show you the Perl 6 code to do it, so that you believe that it works. Okay, so here's our text on the right that we're parsing. The slim text is HTML, head, title, body, and on the left, we've got two things that are going to sort of keep going. We've got a stack that we're going to push and pop from, and we've got a tree that we're going to connect to when we hit indentation in text on the right. Okay, so let's go. First line is HTML. Indentation is at level 0, and there's nothing on the stack, so we push an HTML tag onto our stack. Then we move on to the next line, where we have indentation level 1 and stack 1. So a reminder of the algorithm, you want the level of indentation to be the same as the stack. So if it's the same, the stack is 1, indentation is 1, you're good. When indentation gets too small, that's when you're going to change things. Okay, so indent 1, stack 1, we push head onto the stack. And we move to the next line. Okay. Indentation level 2, stack 2, it's the same, so far so good. So we push title onto the stack, and then we set the title, we run into text. I'll skip that for this demo. And then we move on to the next one. Okay, now something changed. Indent is now 1, which is less than the stack, which is 3. So, because the indentation is less than the stack, we pop from the stack twice. Okay, so we go pop, pop, and we put it down here with the tree. And every time we pop from the stack, we connect a node with the node before it. So title is connected to head, and head is actually connected to HTML. Okay, so now our stack is down to 1, and our tree has sort of looks like a linked list at this point. Okay, we move on to the next one, which is H1. Oh, sorry, and we push the body on afterwards. Then we move on to the next tag, which is H1. Okay, again, now we're back where we have indent and stack are the same. So all we have to do is push the H1 on, and then we run into the text, we set the text of the H1, and then finally we get back to level 0. Once again, indent is below stack, so we are going to pop from the stack 3 times and attach these. So we once, pop twice, and then, so these are connected to each other, and then when we pop the final time, we're connecting to something we already have, so we end up with the DOM. Okay? So here's our DOM tree, HTML, head, title, and HTML body, H1. So it's a little tricky to walk through that, but what's kind of cool is you can apply the same thing to making an abstract syntax tree when you're parsing a language. I'm not going to do that. Okay, so what does this look like in Perl 6? So now that you know the algorithm, it's actually really straightforward. So here's our node class. The node class has a tag, which is a string. So again, these are optional, but these are types that you can put there if you want to constrain the types of your attributes. So we have a tag attribute. We have a text attribute. IsRW means that there's going to be a read-write accessor, and we need that for text because we're setting the text after we put it on the stack. And then we have a parent, which is another node, and we have an array of children. So this is a data structure which has it's a tree, and you have sort of pointers in both directions, right? So you have a pointer to your parent, and you have an array of children. The DOM class, so we have this stack here, which is which we're going to use. We're going to keep track of this while we're parsing, and then we have the top of the tree here, which is a node. So the my declares just a lexical variable, and then has declares an attribute. And so now, okay, just to refresh your memory, the slim grammar has tag, text, and indentation, and so we need to make 3 methods, one called tag, one called text, one called indentation, which say what happens when you reach those particular points in the grammar. Okay, so back to the algorithm. Rule number 1, when you see a tag, push a new node onto the stack. So here we have a method tag. The argument $/ is conventionally used to represent the match object. So this is what was captured that comes in. It's not exactly a string. It's a match. So if you want to set the tag to it, you have to use this tilde, which will stringify it. The colons are another way of specifying parameters. If you don't like parentheses to wrap your arguments, you can use a colon instead. So this makes a new node for a particular tag and just pushes it onto the stack. Okay, when you see text, set the text of the top node. So here we have a method called text, and we just say the top node, you say *-1 to reference the top node, .text equals the incoming text. Okay, so not that much to it. And then the trickiest part is what happens when you see indentation, because now we have to pop until the size of the stack is the same as the level of indentation. Okay, so basically, once you sort of say it explicitly, it's not that bad. While at stack is greater than at $indent. Okay, so there's a little bit of magic here because the $indent refers to the element of the match object that's named indent. So before we started this, you saw that there was an indent in some of the matches, and that'll tell you how many levels of indentation you have. So that $node is popping off of the top of the stack. And then this with essentially is just saying make sure it's defined. So it's kind of like if and then do an assignment, but only if it's defined. So we take the top of the stack here and we assign the node, the parent of the current node to be the top, and we take our node and we push it onto the children of that node. Okay, so that's about it. There's also a way to dump, which you can do recursively by printing out different levels of indentation. I'll sort of skip through that. But all in all, the code is not too bad for doing all that parsing. Okay, and here's what you get. Okay, so for a couple minutes here, I'm going to say a few slangs. Essentially, slangs are a structured way to modify the grammar. So Rakudo implementation of Perl 6 uses NQP, which has Perl 6 : grammar, which is just like the grammar that you just saw, except it's actually parsing Perl 6, and you can mess with it. So this is what you could do right now with slangs. So at the beginning, in the begin block during compile time, if you print out the keys of %lang, you'll see Perl 6 grammar, Perl 6 actions, and all of the things that are being used to parse your current program. They're also available in variables called $tilde, named after the different languages. So $main refers to the parser of the main program. And you can get the grammar, and you can get the actions. So if you want to see, this, by the way, is called the language break. So all these different languages are being used together to parse your Perl 6 program. So if you want to change one of them, first, if you want to see what they look like, you can say --target equals parse, and you'll see the parse tree that's generated while your Perl 6 program is being parsed. Then, if you look in the source for Perl 6, you can see the definitions of these, and they look just like the grammar that we just made up. So you might see, so they have these things like statement, statement list, name, identifier, and if you want to modify it, like let's say instead of sub, we want to use the word lambda, then essentially you can redefine the token. You can say this token now, instead of matching the string lambda, matches the string, instead of sub, matches the string lambda. Very quickly, there's a handy operator for taking a grammar, just like you can take a class and apply. We just saw something called a partial class. It's like a little piece of a role. So Perl 6 has something called but, which says make this little anonymous role that has these methods and override those methods in this particular object. And you can do the same thing with grammars, where you can override a few tokens in a grammar. So long story short, you say lang main equals main grammar, but this is what my subs look like. They start with lambda instead of starting with sub. So that's sort of a long explanation for something that sort of makes sense at the end. But just kind of changes one little piece of it. I'm going to finish real quick. I'm almost out of time, and then I'll see if I can give you a question. And then after that, you can say lambda foo, and instead of saying sub foo, and it'll declare a sub for you. And by the way, if you put it somewhere else, these changes to the grammar are lexically scoped. So inside a scope, you can use the grammar you just made up. There are a few examples of slangs in the ecosystem already. I won't talk too much about those, but you can look them up. There's still some work to be done for syntax for using slangs. But all in all, they're there, they exist. And in conclusion, we've seen some examples of creating informal DSLs using changes to the syntax by parsing something externally or by modifying